Well, as you can see, my only merit is to have very good friends who praise my merits that I don't deserve. Thank you very much for being here. This is the, let me see if it's okay, very good. So again, inspiration is the motto of this section of the conference. I want to tell you a little bit about a few engineering cases where inspiration came to us, and we were able to modestly push the envelopes of our work as engineers. And as you know, when inspiration comes, they say that it needs to find you working. So after every inspiration, the engineer's work means that you still have to spend many, many hours developing your design. First, just a little bit about FERROVIAL. Most of you know us. In operation since 1952, market capitalization around 19 billion euro. These are the countries where we have a presence in the world, and we are very focused on the USA nowadays, which represents more than 40% of our activities. So that's all that I want to say about FERROVIAL. Let me move on to the inspiration examples. I think we are running short of time, so I'm going to skip this one. First inspiration, structural, and as you will see, I'm going to go from the more small scale examples to the larger scale examples. And if you bear with me, I will finish with a very large scale example, which is not strictly related to engineering, and then with that I will end my presentation. So first case, a structural project. This is a bridge in the Canary Islands that we designed in-house. By the way, we work in some of the testing that I'm going to show with the Instituto Eduardo Torroja, and it's the first example of inspiration. You can see, I mean, the bridge relies on modular construction, heavy prefabrication. It's almost verging on the field of ABC, accelerated bridge construction. And I want to focus on the 4 steel tubes that are supporting the deck. And I will tell you, once the video is over, I will tell you a little bit about it. As you know, traditionally, engineers have relied in shear studs or shear connectors to make sure that the concrete inside the steel tubes and the steel work together. And this is, I have here, I'm going to show you a little prop. So just to make it more fun, this is an actual, a real scale size of each one of those steel tubes. You can see the concrete inside in the connector. So here the idea the inspiration was, can you do something with expansive concrete, so to try and get rid of the shear studs, and of course with a proposition like that, as the responsible engineers, you need to start testing. These are the tests that were conducted at the Instituto Eduardo Torroja. You can see, of course, you need to model temperature effects, both uniform and non-uniform heating, to make sure that there will be no slip between the two materials. And in the end, this was the result. Concrete filled steel tubes without stud connectors. And I thank very much Javier Gras, who's here, one of my collaborators, for carrying this over all the way from the office. So next, going up one step, we are moving more into the field of conceptual analysis of potential engineering solutions. As you know, soil structure interaction is an important issue. We deal with, Hugo is going to remember this case because we worked together on this problem. Here we modestly push the boundary of soil structure interaction, making work together geotechnical models and structural finite element models. As you know, geotechnical FM models can be very good at depicting the soil properties. You can make them all as complex as you want, nonlinear soil behavior. You can have the piles slide with respect to the soil to model negative friction, what have you. But those models are not so good in representing the structure. And for structural FM models, the opposite is true. So this was the first case where we coupled both models together. And this is a view of the geotechnical part of the model. I'm going to run a very simplified simulation. This, so to speak, would be the first iteration where you have in FLAG, in the geotechnical FM model, and the building is modeled in a simplified form. The drill shaft foundations are modeled in great detail, and then you start the execution of the two tunnels that are going to run under this building, and in so doing will cut through 67 piles of the foundation. It's a partly historic building in London. It's partly, as I said, classified as a historic building, big structural masonry walls. So of course you want to make sure that nothing happens to the building, and you need to design whatever evaluate potential damages and design mitigation activities. Red here is good. Sorry, it should be the other one. Red is zero settlement. And now we start the excavation of the tunnels. Of course, you see the arching effect of the building, and in doing so, you can calculate essentially the reactions, the loads that each of the drill shafts is carrying. Of course, a model like this, prior to this, there was extensive pile load testing on the site, because with such a complexity, as engineers, you need to make 100% sure that you are representing reality. This is the structural part of the model. This was done in Sophistic. You can impose the movements of the drill shafts onto this model, which is much more detailed from a structural standpoint, and then you can run the structural part of the model, obtain the reactions on the drill shafts, and then the process starts again. And at this time, we did the combination of both models in a very crude way. Nowadays, software has been developed that can make them run seamlessly, and you can cycle through as many iterations as you want. This opened a completely set of new opportunities for us, and we have used it in several complex geotechnical structural analysis. And of course, ultimately, you can check your failure criteria, in this case for some of the masonry walls in the building. Next example, and this has nothing to do with structures. It's really from my own field. And we're going one step in terms of the scope of the project. This really is looking at the whole concept of how the project should be conceived. Two important concepts here, public-private projects, or PPPs or P3s, are projects which involve not only construction, but also the financing and the operation and the management of the asset over many, many years. This is, in particular, a toll road in Dallas, in the USA, and there are two interesting concepts associated with this type of P3 that our company has developed many times in several places, including the US. Traffic risk means that your revenue is associated to how many cars drive on the facility. So a project like this, a concessionaire should treat as you were the owner of a restaurant. You want to entice customers to drive on your facility. You want to provide a good service so that they come back. The other interesting idea, and this is a concept that is becoming very common in the USA, is what is called managed lanes. This means that you take an existing freeway, which is heavily congested, and then you add some toll lanes, but keeping some of the non-toll, the free lanes, so that the user can decide whether to drive on the free lanes or drive on the toll lanes, and in that way he pays a charge. It's interesting because rates change every 5 minutes, and it's like in a restaurant. You see the menu, and before you enter into the managed lanes, there are big signs that tell you how much you will pay if you enter at that time. There's a mechanism whereby if congestion on the toll lanes goes up, then you are allowed by contract to raise your toll rates. That, due to the elasticity of demand, means traffic comes down, and then you can guarantee travel times to your users. So in a case like this, the challenge is you want to try and provide as good a service as possible and improve connectivity. And in this example, the construction cost of this project was approximately $1 billion. You can see on the left, I don't know if is there a laser here? Oops. Good, okay, excellent. So you can see red is the important color. Red are the managed lanes. These are the toll lanes, the lanes that generate revenue. This on the left is the project as we received it from the public agency. The toll lanes go into downtown Fort Worth, and very key aspect. You see here IH-30. This is a very important transportation corridor between Dallas and Fort Worth, key in the area. This project was not doing anything to reduce congestion in this important interchange or alleviate congestion on IH-30. Why? Because really the challenges, it's not that the people who thought about this project for 15 years, maybe they thought of it, but there were two difficulties. One is the land occupation. It was difficult to get additional right-of-way for construction in that area. And also during the public planning process, sometimes, quite often, there is not an advocate to treat a project like this as a business. So our solution is shown, this is how the project has been built, is shown on the right. Managed lanes were extended down farther south, and really this is where the inspiration came, that there was this little section of freeway, Spur 280, already connected to IH-30, so the eureka moment here is to connect the managed lanes to this short spur, and this is what provided complete connectivity with IH-30. Nothing to do with the structures. This is a simple idea, but someone has to see it. And then, of course, behind or following this, there is huge work. You need to spend many hours of good old engineering practice, making sure that everything could be built without one single square meter of additional property, which really this was the effort and the biggest merit of my team in this project. Interestingly enough, this means with all that red that we added, the construction cost of the project went up by $100 million. But the extra revenue was $250 million. So it means that by making a project more expensive, you are making it more financially feasible, which is an interesting idea. And this is something that, when looking at traffic risk, managed lanes, P3s, is a key aspect. You need to change a little bit the mindset, and sometimes you don't want to only make your project efficient, cost competitive, and so on. Sometimes you want to increase cost, making sure that you attract more traffic. And the interesting thing is that if you attract more traffic and serve your interest as a concessionaire, you are also reducing congestion in the nearby and in the free roads. So you are working also for the drivers who do not drive on your facility. And I think I have the last one, the last example, very removed from the field of engineering. Please bear with me. I don't know whether this is too much, but inspiration, I was reading the definition of inspiration in many dictionaries, and inspiration, there is one thing in common. Inspiration is a motion not only on the intellect, but on the heart as well. You can be inspired to altruistic behavior, you can be inspired by a person, and to me, what I'm going to show is a big source of inspiration. More, and I apologize because it is very removed from the field of engineering, but I think it might be, you know, after the excellent presentation by Mike Sly, what I'm saying here, it's very humble, so this is not anything that has to do with my potential achievements, but it makes me very proud as a human being and as an engineer, and it's a big example of you know, how good we can do professionally. More than 2,000 years ago, these three gentlemen measured the actual radii of the Earth, the Moon, and the Sun, as well as their distances. No telescopes, using the naked eye, using the newly discovered field of trigonometry. It's really very inspiring. The methods they used were incredibly ingenious. I'm sure all of you know about this. It's always good to go back to the internet and refresh what they did, and this to me is a great source of inspiration. I wanted to leave the group with this idea, hoping that, you know, the sessions in these 2 days are very fruitful, and convey this, my thinking that to me this has always been a big source of trying to be better as an engineer and serve society. And on the other hand, engineering is a lot of fun, so that's on a selfish side, it's important too. Thank you very much.
Thank you very much, Torole. Good afternoon to all of you. Well, I'm talking from a construction company, and because of that there comes the title. We must bridge the gap between the concept design and the reality. I think the contractor has always a part in the reality, and the concept design is at the very beginning. And then the more both approach each other, the easiest is the way from going to the concept to the reality. And in this direction, it plays a big role speaking a common language and be able to prepare a common playground. In this way, just having in-house engineering skills in the construction companies helps very much in speaking that common language. When I was told for a so short time, so what can I say? Well, I decided just to choose 5 flashes of 5 activities that we lived that are interesting concept designs that went into the reality, where FCC, together with the consultants, together with the engineering, solved problems that sometimes arose during the executions and were not directly derived from this conceptual design. I'm sure Professor Corres will recognize some of his really nice values that are in the part of these activities and some of the attendance too. I will go a little bit fast to this. Well, I will talk first about the Mersey Bridge. The Mersey Bridge is a really structural breakthrough within a challenging environment. It has just been awarded by IAPSE with the Outstanding Structure Award in 2019. Obviously, you can see from the picture there's a cable-stayed bridge with 3 pylons, but also is placed in a very sensitive environment in estuarine waters. That means that the ecosystem where the bridge is placed is extremely sensitive, with a really complex biological structure, and it was a real challenge just to be able to tackle this complex structure in a so complex environment. Of course, the bridge was addressed with the technical tools that needed for the structural, but in parallel there was an environmental management scheme that was key in going from the concept design to the reality. The construction was carried on by in balanced cantilever with a temporary trestle, and obviously this trestle was on piles, and after finishing everything had to be removed. The aim was having the minimum interaction with the water flow, the water dynamics inside the estuary, and with the also retired, once retired the structure, everything was recovered. In parallel, several PhD theses were performed and sponsored by the construction JV on the ecological values of the area. And also, there was a continuous interaction with the population in the surroundings. There was a communication in both directions that made really this work a success. Other one is the Almonte Bridge. This is a high-speed railway bridge. It's an arc with 384 meters of span. When it was finished, it was a world record in concrete bridges for high-speed railways, and now probably there are other bridges that have some more span. And the cross-section is quite complex. From two hexagons that are separated in the abutments, they go to a single octagon at the key. That's why it's a little bit complex. It was overall winner AC Excellence in Concrete Construction Awards in 2018. You can see at the center the change in the formwork from the section and the abutments just changing smoothly to the octagon. You can see at the right just the transition. It was a complex formwork that we were advancing there. And the construction was carried on by two cable-stayed cantilevers. And there came a structural challenge coming from the construction process, from the method statement, that obviously we needed temporary towers for the stay cables for being able to connect the bridges. That was very complex at that site, and let's say the key of our in-house team, the special works team, was a really ingenious frame that allowed us to, by vertical rotation, place the erection towers that served for the auxiliary cables for being able to construct this bridge. Another experience is the Riyadh Metro. Here we will see the interaction of the construction equipment with the design. The original design is upper up the left with a really complicated beam for handling it, for pouring the concrete, for placing it. And some of the lines were directly constructed with this solution. But in our line, our joint venture of construction decided to go a little bit beyond, trying to simplify and go on. Then also with our engineering partners and our in-house engineering, we did a first review that was changing that complex beam for a caisson beam where the webs were more directly closer to the loads of the railway, and then structurally it has some advantages. Several sections were built with this solution, with precast elements for the full span sections. The question is that we had several lines with a lot of this kind of viaducts, and this solution required very special erection equipment. Special erection equipment that means it took time and a lot of money to have many more teams available on site. So in order to strengthen and make more reliable the construction, a further step was done. That's splitting this big caisson beam in two half beams. So the section could be addressed with conventional erection equipment. That means a more robust structure. It's easier to replace a crane than a launching gantry, and then this allowed to tackle the challenge with more reliability in time and in cost. Obviously, it was necessary to recover the original aesthetics. That was no problem. You can see there how it was recovered is practically the same as the one in the original design. Another experience was the Fernando Reig Bridge in Alcoy, where the project consisted in the replacement of the full set of cable stays of a cable stayed bridge that had several decades of life. Then there was a breakage in one cable, there was structural inspection, and then the administration decided to change all the cables. Then we started to work with the designers together, thinking in the problem, and well, it was developed a procedure, of course, of relying the tension while controlling from the towers behind with jacks, controlling the reaction in the adjacent cables. But in the next stage, when we were going to rely that tension, it happened that the tension could not, in general, except in very few cases, be released as it was prepared, with the jack simply taking with the clamps the cables. There was a general lack of free length for anchorage, and also some of the cables were corroded. And then that everybody had to think a lot to go for other more comprehensive solution. Well, the final alternative method was based on friction clamps, just to take the cable, and then with a capacity of 5,000 kilonewtons, actuated by jacks and rods. So the procedure was the removal of the duct that protected the cable and also of the cement grout, because there was no friction capacity for working with the clamps. A special compound was designed for filling that gap and clamping the ducts. And then with press-testing bars, the tension was transferred to these bars. Then the cable could be cut without tension, and then the tension could be released smoothly, just reproducing the general structural scheme. You can see there the device with the clamps, the press-testing rods, and all this situation. Well, we have to say that the scheme was really successful. Now I will go to a couple of R&D projects. R&D project seems more close to the scientific side, but from the construction part, from a contractor company, let's say the so-called the valley of death seems wider, but sometimes a good interaction with the researchers, if you fix well real problems, you can find answers in the researches. There's one paper that from 1920s that called "The Usefulness of Unuseful Knowledge." Sometimes researchers are researching in topics that they don't know really. They have clear application of are the answer to real questions that are in the industry, and that communication is sometimes very fruitful and provides very good results. This is a centralized system. It's a R&D project that's ongoing now. It's a system for monitoring the linear infrastructure construction based on well, here we say high-performance drones. I would not say that after hearing the presentation by Professor Ratti. They are simple drones. They are simple drones that one of the aims of the project is the development of the drone itself. A drone capable of taking a lot of data collection and for the inspection of linear works. In this case, the drone collects the data, and the second stage of the project is linking that to a 3D model, to a GeoBeam, and the process of that model is not addressed to a diagnostic or to design. It's really addressed to the follow-up of the construction. It's just having the advance of each one of the parts of the construction scheme. This is an ongoing project. And by last, of course, my activities in Piang oblige me to put something with salt water. It's a case where, from the concept to reality, the barrier is in nature. You have the forces of nature that are intervening in this step. This is typically the case of vertical breakwaters constructed with reinforced floating concrete caissons in exposed marine climates. In this case, you have to perform maneuvers of towing caissons, placing them by sinking and ballasting with salt water, and with, let's say, an accurate placement. So you have to build a breakwater that's a straight line with some reasonable tolerances between caisson and caisson. And what happens is that in many locations in the world, this is a really difficult job because you have a very few weather windows where you can work with this accuracy. In this case, this project was defined after our experience in several real projects where we were lacking some kind of technological development that could give us some reliable procedure to do this, and a reliable procedure also for analyzing the real climatic thresholds of that maneuver. The plan was a real instrumentation of real caissons in a real site, in the extension of the port of Granadilla in Canary Islands, and the caissons were measured, the accelerations and all kinds of movements, and also the tensions in the mooring and towing lines during the phases of towing, storing, and placement by ballasting and sinking. Afterwards, just after those data, a model test process was developed in the large ocean basin of the Cantabria Institute of Hydraulics at the scale of 1 and 12. More than 100 simulations that allowed to obtain the parameters for making a tailor-made adaptation of advanced 3D models for marine structures, so we could measure movements, stresses, tensions, and we could analyze the maneuver. And then, through this process, the final step is a methodology and a mathematical simulator for the stages of towing, storage and placement, and also a full operational system as a tool for analyzing alternatives for the maneuver of placement. So this is really a success. This project is already finished, and we are in ongoing projects that have got from this moment. And well, these were the few ideas I wanted to shift to you very fast. Thank you very much for your attention.
Good morning. Thank you for coming today to this Torrojas Institute this morning. I hope that you are enjoying this Congress and also Madrid City. Let me introduce myself. My name is Mariano Martín, and I'm in charge of the Structural Engineering Department in ACCIONA Engineering. What I'm going to try to do this morning is in only 15 minutes to give you a general overview of what is ACCIONA, what are our core, I'm going to try to sum it up in only 2 words, how are we divided, and finally, we are going to land into the engineering and innovation part of the company. Let's start then with the first part of the presentation. What is ACCIONA? Okay, ACCIONA is a global company. We are a global leader in infrastructure, water, services, and renewable energy. We are more than 38,000 employees all around the world. This is a company with more than 100 years of history. And we invested last year, in 2018, more than 225 million euros in innovation, research, and development. Where are we located? Okay, mainly we are located here in Spain, but we work all around the world. Now we are focused in the north of Europe, mainly in Norway, Canada, and Australia. But as you can see, we are based in all around the world. Let's go to the second part of the presentation. If we have to sum up the core of our company, we would say that ACCIONA is a sustainability and innovation company. Since 2016, we are a carbon neutral company. Okay. We have a 2020 sustainability master plan. We are very worried about mitigation of climate change. For example, this week, our president, José Manuel Entrecanales, is in New York in the meetings related to climate change. Okay. We are focused against climate change, water stress, you will see during the presentation, and our aim is to design infrastructures suited to the new circumstances. Moving on to the other part, innovation. We are involved in more than 123 projects related to innovation. And here in Spain, we are the 6th company related in innovation. Okay? Moving on to the next part of the presentation. ACCIONA is divided into two main branches, energy and infrastructure. Related to energy, I would like to highlight that we only invest in clean technologies. Okay? We are really strong in the wind and PV, photovoltaic, but only we have assets in hydro, biomass, and thermosolar power plants. Now we are the owners of more than 9,000 of megawatts, and we have under construction 1,000 megawatts. You can see, for example, some examples of PV plants in Mexico, Egypt, also wind farms in Australia, the United States, another example of a hydroelectric plant here in Spain. Okay, this is the energy part. If we move on to the other part, the infrastructure part, it is divided in the construction, concessions, water, industrial, and services. Starting with the water part, our aim is to fight against water stress in the world. We have constructed, or we are constructing more than 75 desalination plants. For example, with ACCIONA Engineering, we collaborate with ACCIONA Water. We are designing a lot of desalination plants in Middle East, namely Jubail in Dubai, in Arabia Saudi, Al-Khobar. Also, we are involved in the construction of more than 400 water treatment plants. Now we are working hard in the Vancouver, with Metro Vancouver, in Lionsgate, water treatment plants, and completely focus on research and innovation. Just to give you an example, we have a patent in an RO system, reverse osmosis system, and we have our own system to be applied in the desalination plants. If we move on to the industrial part, most of our projects are EPC projects or turnkey projects based on energy. For example, from ACCIONA Engineering, we have collaborated with the industrial plant in the construction of a lot of photovoltaic parts. Last year, we finished Reynosa and Mesalapad wind farms in Mexico with more than 200 wind miles. And of course, with the thermosolar plants here in Spain, Ormijana, Olivenza, but also in Morocco and South Africa. Service. Only I'm going to give you one date. Since there are a lot of young people in this Congress, we have started here in Madrid with a motor sharing service. I'm sure that you have seen a lot of motors, all electrical motors, and strongly invite you to use these motors this afternoon in this Congress. And concessions, it's the other part of the infrastructure. I'm going to skip this part and going directly to the construction part of ACCIONA infrastructure. Our aim is the specialization, the self-performance in-house, and of course the creativity and innovation. We are involved in the whole life of the projects from the very beginning with the opportunities, with the tender. Then, of course, during the execution phase, we carry out the detail phase. We help during the construction phase with our technical assistants, and of course, in the maintenance phase and operation phase. Here you can see two examples. In the upper part, you can see the viaduct of the Expo 2020 metro line in Dubai. We are finishing this bridge. And in the bottom part is the Walterdale Bridge in Canada. Okay, the construction part is divided into three: road and bridges, tunnel and railways, and special projects. Related to road and bridges, I'd like to highlight in the bottom part, you can see a cable stay bridge under construction in Philippines. It's Cebu Bridge. I will go back to this project later. And also, I would like to highlight the innovative technology that we have related to trash block system to push the bridges. It is completely patented by ACCIONA. Moving on to the railway department, just to highlight that we have developed tunneling machine control center. Using big data, we are able to get all the data that come from all the TBMs of ACCIONA all around the world. With our own system, we have developed software to be aware of what is happening, and on real time to be able to make a decision. Here I would like to highlight the follow line project, which is under construction. This is an EPC. ACCIONA Construction with Gela are the construction company, and ACCIONA Engineering is the engineering firm that is in charge of all the design of this project. Let's move on. This is the special projects area. I would like to highlight that we have constructed more than 60 harbors around the world and more than 50 dams. We have constructed the largest reservoir in West Europe. It is located in Portugal, Alqueva Dam. Okay, and also we are the owners of 3 caissons that are able to construct docks. Hugo, Thor, when I was 2 years ago in the conference related to submerged floating bridges, I think that the idea will be to use this kind of devices, because we are able to construct the docks in the sea, and the idea will be to adapt that kind of caissons to do the future bridges below the sea. Okay, we are arriving to the last part. This is the engineering and innovation part. ACCIONA Construction has 2 companies, ACCIONA Engineering and a technological center. I'm part of ACCIONA Engineering. We are more than 300 people here in Madrid. We are in charge of the technical services of the construction company. We help the company, for example, to study construction processes. You can see here the abutment of an arch here in Spain. I would like to highlight our latest device. We are the designers of the ACCIONA beam launcher. We are going to use this beam launcher completely designed and fabricated in ACCIONA in the bridges of Cebu Bridge. I've told you before, the cable stay bridge. We have thousands of kilometers of beams to put on site, and this is our latest innovation. Now it is traveling in a ship from Spain to Philippines, and we hope that next year we will use this machine successfully to put all the beams on site. Moving on to the technological center, we have a center here in Madrid with more than 100 people working in innovation related to construction, materials, construction processes. And together with the engineering firm, the innovation part, and the construction company, to finalize, I'm going to show you some real projects where creativity, innovation, and engineering are together. The first one is a carbon fiber bridge. It's located here in Spain, in the north, in the Cantábrico-Asturias highway, 45 meters in 4 spans, 10, 13, 13, 10. Okay, it's made of 3 continuous carbon fiber beams. You can see the construction process, also the deck view from the bottom part, and finally the loading test. It was made in the 2004, and it's working perfectly nowadays. If we move on to the next experience, then we continue with a hybrid carbon glass bridge here in Cotolengo in Algete, 20 kilometers away from this site. It was 2007. We used 4 hybrid isospan U-beams, and the same, you can see the construction process. Also, the way that we put on site the deck panels with only 2 people, and a general view of the bridge. Moving on, then we continue in Africa, in Ibunji, in a mining hydroelectric plant with a hybrid carbon glass. Due to the location of these projects, we weren't able to stretch a steel girder or concrete, and we decided to fabricate here in Madrid 2 hybrid U-beams and to transport in a ship. It's only 17 meters isospan and 6 meters width. Related to footbridges, in 2010, we constructed here in Madrid over the Manzanares River a footbridge, 44 meters span, made of carbon fiber. You can see the pictures in a U shape. You can see the construction process with only one crane. We were able to put on site all the deck. And the final view, you can visit this footbridge here. It's located very close to this place. In 2011, we continued with a footbridge, a stress ribbon footbridge in Cuenca. And the particularity is that the cables of this stress ribbon footbridge are made of carbon fiber. You can see the cables in the first pictures from the bottom part of the deck. You can see the cables of carbon fiber, then the construction process, and the final view of the footbridge. At the end, due to the handrail, we have to put a really high rail to avoid people to throw through the air. But I think that it was a really nice result. And related to footbridges, I would like to conclude with the latest, with the first 3D printed concrete made in the world 2 years ago. It is almost 12 meters span. It is located here in Alcobendas, 15 kilometers away. You can see a detail of the 3D printed detail. This afternoon is going to be a workshop related to this kind of technology. Then you can see the loading test. We use it containers with water just to see the behavior of this footbridge and the final view. ACCIONA has 3 concrete 3D printers now. 2 of them are located in Madrid, and the other one is located in Dubai. And we are starting now studying the 3D printers in metal, in steel. Okay, and we have arrived to my last slide, just to give you a general overview of other innovative projects. For example, here you can see the waterproofing that we have to develop in a tunnel, in Pajanes tunnel here in Spain, in León, Asturias. We used glass fiber panels. Then you can see a composite lighthouse here in Valencia, in Spain. The next one is a dolphin. We have 3 of them in the Canary Island, made of composite glass fiber. Of course, glass fiber rebar used with when the TVM is going to cross the diaphragm walls. A lot of projects with fiber reinforced concrete, namely in Norway. Of course, fiberglass stairs here in Metro, working in as a cantilever, as we saw yesterday in your presentation. We also have used glass fiber in sheet piles, and of course, our latest machine related to innovation, the ACCIONA beam launcher. I hope that you have enjoyed the presentation. I hope that in the future we can collaborate together. Okay? Thank you very much for your attention.
Good afternoon, everybody. It's a pleasure for me to be here with you and introduce my company, DRAGADOS. First of all, just a few information about the company, because you might not know it. So, DRAGADOS belongs to ACS group. It's a construction group, an international construction group. DRAGADOS is the main construction company. Also, Hochtief is part of that. DRAGADOS is in the construction area, but there are also a service area and also an industrial. ACS is the first company, the construction group in Spain, as you can see here in this rank. We are the 7th in the world, but pay attention that the first 5 are Chinese companies, so Olive and C is ahead, is here. And in international, as international contractors, we are in the first position because we work all over the world, as you are gonna see. In this map, you can see only the presence of DRAGADOS, not all the ACS companies. But as you can see, we work in Spain, in Portugal, Poland, South America. But our main market is, without any doubt, North America, the United States, and Canada. It's approximately the 70% of our work is there. So this evening, I would like to talk to you about our experience building cable-stayed bridges. We have finished in the last 5 years 4 cable-stayed bridges, as you can see on the slide. In 2015, we finished the first important one. That was the Cádiz Bay Bridge, located in the south part of Spain. It is the longest span in Spain, with 540 meters long. The next one was in 2017. This is the Queen's Ferry Crossing in the Firth of Forth, great places for bridge lovers, let's say. It's in Scotland, and it's a multi-span cable-stayed bridge with 2 spans of 650 meters long. Actually, this bridge holds the record for balanced cantilever construction, because it had 2 cantilevers of almost 325 meters long, which was really a figure. Last year, we finished the widening of Rande Bridge in the northern part of Spain. It was the first time ever a cable-stayed bridge is widened by placing 2 new decks at both sides of the existing bridge. That was a very interesting work also. And the last one has been this year. This was the new Champlain Bridge in Canada, in Montreal, over the St. Lawrence River. Although this span is shorter than the others, with only 240 meters long, this was probably the most difficult bridge to erect, because some considerations we will see later. So talking about cable-stayed bridges, we still have 2 under construction. This one is between the border, in the border between Canada and the United States, over the Detroit River. It will have 143 meters long, and that will be the longest cable-stay span in North America. So we are still under construction. We are with the foundations. And the other that we are building now is the Harbor Bridge in Texas, in the United States. This is a concrete deck and will be a world record in cable-stayed concrete deck, with this over 500 meters long. So, as you probably know, erection procedures are paramount when dealing with these cable-stayed bridges. Why? Well, because 2 reasons mainly. Because we have to deal with a structure that is not finished. The structural layout of the bridge is not the final one, so the situation is, let's say, more poor. And in this situation, with this non-finished structure, we have to deal with really heavy loads. Heavy loads that are a lot bigger than the loads that are going to be over the bridge during his service life. So we put together this non-final structural situation with these huge loads, and we have something important to solve. So the erection procedures that we use for cable-stayed bridges, well, the most used one is the cantilever procedure. We have 2 options for cantilever method. We have the balanced cantilever, when we have at both sides of the pylon cantilever that have to be balanced, like in Cádiz Bay Bridge, in this picture that you see on the screen. And the other option is the single cantilever, and it's when you first erect the back span on a shoring system, and when the back span is finished, you start to erect the main span with the cantilever. There are another difference in this cantilever erection according to the segment or the kind of element we lift to the deck, and we have these 2 options, the segment erection and the stick build. In the segment erection, you have to build the whole cross-section, a segment of the bridge, of the deck, you prefabricate it on a yard, and then you lift all together. This is the segment erection. And the other is the stick build. In this situation, you just erect you lift to the deck single elements, and you fabricate, let's say, the cross-section up on the deck. In this presentation, I'm going to focus on the segment erection because it's the most common one and is the method we have used in these 4 examples that I'm telling you about. So, talking about this erection procedure, so cantilever method together with segment erection, we have found that there are 2 problems to solve. Remember that it's important to build these bridges because we build a bridge, we learn a lot of things, so for the next one we know more and so on. So we are learning in each bridge, so the next one we will do even better than the previous one. So we have found that these two problems are paramount to solve, and this is how to transmit these huge erection loads that we have over the non-permanent, non-finished structure. This is the first question to solve. And the second is how to assemble this segment that during the lifting deformates due to its self-weight to the structure that has a different shape. So these are two problems that we have to solve. So let's see both of them because they are interesting. First of all is how to transmit direction loads. Well, we need a special device. We can call it lifting gantry, erection traveler. There are many ways to call it. But we have to think how to design it because it's paramount to the impact on the structure. So think that the load we are going to transmit to the non-finished structure is the weight of the lifting gantry together with the weight of the segment, which is a big amount of tons you are going to see now. So the idea is to transmit these really heavy loads directly to the resistance elements. So if possible, to the cables, to try not to oversize the permanent structure. So this is the main idea. So as you can imagine, there is not a magic solution, an only solution, and we are going to see now how we have solved this problem in these 4 bridges that we have finished in these 5 years. First one was Cádiz Bay Bridge. Here you have the lifting gantry. We designed this lifting gantry in-house in DRAGADOS. And in this case, this lifting gantry was designed not only to erect the segments, but also to lift the full depth precast panels. That's the reason why this lifting gantry was so heavy and so big. It weighed over 500 tons for a maximum segment weight of 400 tons, which is quite a big. So in this case, you see here the lifting gantry. It moved over these rail beams. The rail beams were supported at the diaphragms of the steel structure, and the diaphragms brought the load until the cable stays. But that was only for, this was the support system only for the movement of the lifting gantry, because when a new segment was going to be lifted, imagine that in this situation we had to withstand almost 1,000 tons, so 500 the lifting gantry plus 400 of this new segment. In this situation, the lifting gantry was designed to deploy a new support, as you can see here. So the idea was to transmit this really heavy load directly to the state without penalizing the structure of the deck. That was in Cádiz Bay Bridge. Next one was Queensferry Crossing. In this case, the problem was a lot easier to solve because the lifting gantry was very simple. Imagine that for a 50 tons maximum segment weight, the lifting gantry weighed only 215 tons. So in this case, the lifting gantry was located over the resistant part of the section. As you see here in the cross-section, the lifting gantry transmitted the load directly to the webs and to the stays. So in this situation, the situation was easy to solve. Next one was run the widening. In this case, for this widening, you see here that this is the existing bridge and this is the new part, the expanded part. In this situation, we need two travelers to place the new segments because the expanded deck couldn't resist the total load, so we need to share it. And we couldn't place either the lifting gantry in the existing bridge because we couldn't affect the traffic. We had to perform all the works without affecting the traffic at the existing bridge. So we designed this system with these two travelers, the front traveler located in the existing structures and the rear traveler located at the expanded. So here is a sketch of the front traveler. As you can see here, this structure was hung from the main girders of the existing structures, but when a new segment was going to be lifted, these red PT bars were tensioned, so the load of the new segment was transferred directly to the cable stays without affecting too much to the existing structure. Here you have a picture of this front lifting gantry and see how it was rolling below the main girders of the existing bridge. The rear gantry, the one that was located on the expanded deck, was a lot simpler. It was a steel structure over these rail beams. The rail beams were supported at the diaphragms of the structure also. Remember the idea of transmitting the load directly to the resistant elements. But when a new segment was going to be lifted, again, we have a special support to transmit directly the load to the stay without affecting too much the steel structure. And the last one was Champlain Bridge, the Canadian one. Well, this was a very complicated bridge. The geometry was really complex also, and I'm sorry for saying this, but I think the structural behavior was not taken into account in the initial concept of the bridge, so that brought us a lot of problems. Because if you see here, this bridge is made up of 3 independent corridors, a central one and 2 lateral ones. But in the cable stay section, which is this that you have in the image, these 3 corridors are connected by crossbeams, as you can see in this other drawing. You can see also here the 3 corridors, and you see these white elements. These are the crossbeams that connects the 3 corridors, and it's the place where the stays are anchored. So the stays are not anchored in the longitudinal elements, but in these transverse beams, which was really crazy from every point of view. So in this case, the design of the lifting gantry was complicated because we had to adapt to this complex geometry. So since the deck had these 3 corridors, the lifting gantry needed to have these 3 elements also to transmit the load directly to the resistance element that were the box girder of each deck. So again, like in the other bridges, we have these rail beams for the movement of the gantry, but when a new segment was going to be lifted, a special support was used to transmit directly the load to the webs. So that was the first problem, how to deal with these big loads that we have during the erection of these cable stay bridges. Let's see the other. The other is how to assemble a new segment. Of course, we always recommend, and it's always advisable, to perform a trial assembly, absolutely, without any doubt, to make sure that everything matches in the yard. But even performing this trial assembly, when you lift the segment, this segment deflects due to its self-weight, and this shape probably doesn't match with the shape of the already erected bridge. So the idea is to try to lift the segments from hanging points that produces a transversal shape as similar as possible to the transversal deflection of the bridge. So the most intelligent idea is to place the hanging points exactly where the cable stays are. That's the ideal situation, but sometimes this is not possible. So we have to look for the best situation to minimize this difference in the transverse deformation. And it's also important to point out that although we had taken into account all these ideas, sometimes the assembly is difficult, and we need to design special devices that help us to match the splices. So let's see how this problem has been solved in these 4 bridges that we are reviewing this afternoon. First one, remember, was Cádiz Bay Bridge. In this situation, in this bridge, sorry, the cables were located at the edges of the section, so we couldn't place the hanging points of the segments in this situation because, well, we lifted the segment without the concrete deck, and the segment would often resist the load without the concrete deck. So it was not possible to place the lifting points where the cable stays were. So we placed them in the situation where the shape, the transverse deflection was minimum. And we placed them over the transverse diaphragm because in this bridge there is not a longitudinal web along the whole structure. So in addition, to minimize this problem, we adopted some measurements that you have in this sketch here. We place an additional diaphragm at the end of the segment. We place additional webs, also little ones at the end, and we close this lateral box to minimize the distortion of the section. That was in Cádiz Bay Bridge. In Queens Ferry Crossing, the problem was also simpler to solve because we placed the hanging points exactly in the same place where the cable stays were. So the shape of the deformation was very similar in the segment and in the deck. In addition, this deck was really stiff, so the deflections were minimum, so this problem actually didn't exist, and the assembly was easy if we compare with the others. This is Rande Bridge. The widening, in this case, the transverse dimension of the segment was not big enough to present any transverse deflection. But anyway, we place, we lift the segment from its center of gravity to avoid rotations during lifting, and also the hanging points were located where the cable stay was. In addition, we have these lifting beams that you can see in the pictures with this transverse jack that allow us to modify the rotation and to perform the assembly and the splice correctly. These lifting beams were located at the diaphragms of the segment to, well, hang the segment from the resistant element. And the last one, and the most difficult, was the Champlain Bridge. As you can see here, I don't know if you have an idea of how this picture has been taken. We are in the deck, and this is the lifting gantry supported on the 3 corridors. It has been lifted a new segment, which is here. So the hanging points here are very close to where where the stays are, as you can see here. But in this situation, although the shape of both segment and deck were similar, the problem here was that the lifting gantry was really heavy. It was so heavy that the deflection that introduces in the deck was this blue line. So the blue is the deck deformated by the weight of the lifting gantry. The red one is the segment deformated, and you see the shape is similar, but we had to introduce vertical forces to match the splice. But in addition, in this bridge, we have additional problems because of the structural conception of the structure, and is that due to the position of the cable stays that were located, as I remember, at the crossbeam and not on the longitudinal elements, the compression introduced in the central corridor was a lot bigger than the compression introduced in the lateral ones. So the problem in the assembly was that we have to align in plan and in transverse the elements that had not the same shape. So in this case, we had to design a very complex alignment system. We need tailor-made steel structure with PT bars and vertical jacks to match the vertical deflections to perform the splice. But also we need here in the bottom part of the section, we need also a system with PT bars and horizontal jacks to match the plan alignment and also the transverse assembly. So, well, these were the ideas I wanted to tell you. I hope you take into account these points when designing your next cable stay bridge.